Roger Penrose. It's been a long time coming. I've been a huge fan for, I think, decades, literally decades. Thank you and welcome.
My pleasure.
Good meeting you at the Institute for Arts and Ideas.
Lots of people don't believe some of them.
The arts and ideas? What do you mean?
Well, the ideas about cosmology, which I have, which are certainly, people have a lot of trouble believing them. Even though we have good evidence, yeah. But still, never mind.
Is that the torch that you want passed on most? The conformal cyclic cosmology?
Well, I have a trouble because there's more than one thing. You see, one of the things is twistor theory and its progeny. There's been a conference. You see, this is taken seriously in the sense that there has been a conference going on all about twistor theory, not just a conference, but a whole, I think, of a whole term, I think, dedicated to the subject of twistor theory, which is something which I sort of started in 1963, I think it was. And it's had many developments and many offspring, you might say. And it's spread out to have interest in different areas. Now, it's one of the things that I've been working on for most of my life. And I can't explain it without being a little technical. It's just that...
You can feel free to be technical on this podcast.
Okay. It's a bit like... Well, Hamilton discovered quaternions, which was a way of talking about the geometry of three-space, and he introduced this thing called the vector product, which if you have two vectors, well, it's really an algebra of vectors, where you have vectors and scalars mixed together, and if you multiply two vectors, you have this thing called a cross product, which gives you a third vector. Now, this kind of notion is coming in at a different level with what I call twistors, or now what I call bitwistors. See, the twistors, the subject took ages to develop. As I say, 1963, when I first had the concept, so I gave a talk in Cambridge just recently, where I explained the origin of the ideas, and there's a certain, you might call it, slight misconception. There are two different concepts which get confused in twistor theory. And these two concepts are positive and negative frequency and positive and negative helicity.
Mm-hmm.
And the thing is that the positive negative frequency idea was something that I learned from Engelbert Schucking, who was somebody I shared an office with when I was in a group of people working on general relativity in Syracuse, New York State, in the United States. And there were a lot of people working on relativity theory there, and this was, I think, in 1962. And I learned from Engelbert Schucking two things which I found very interesting. One of them was this question of what you mean by what's important in quantum field theory. And he said the most important thing in quantum field theory is the splitting of field amplitudes into their positive and negative frequency parts. You keep the positive frequency and you throw away the negative frequency. And I thought, gosh, that's an interesting idea. The other thing he told me was, and he told me various things, but these were the things of relevance to what I'm saying. The other thing he said was to do with the Maxwell field equations. Maxwell's equations, which are very important. They describe electricity, magnetism, and light. So it's a theory of light as well as how electric and magnetic fields interrelate to each other. Very beautiful equations, which I learned about when I was a graduate student. And I was very keen on the Maxwell equations, especially when you write them in this formalism called two-spinor formalism, which is, I can say a bit more about later. But the Maxwell equations, he told me they are conformally invariant. So they only depend on space-time structure independent of the scaling. So if you magnify the scale up or down, magnify the metric up or down, if you like, it makes no difference. That's conformally equivalent. So the conformal maps are ones, or the conformal transformations are ones which can change the scale, but they don't change Well, they don't change the light cones in special relativity terms. So the speed of light is the same. Of course, light, after all, the speed of light is the same when you magnify and change the scale. But what struck me about these two facts that I learned from here, is there seemed to be a little of an impasse between the two. I mean, how do you decide what splitting the positive and negative frequency? You look at the individual frequencies, which means you do a Fourier decomposition, and you take each individual Fourier component and you split that into its positive and negative parts. That's not conformally invariant. You do a conformal map, conformal rescaling, the Fourier decomposition does not go into itself. And so I thought it would be lovely to have a way of looking at this, which is they come together and you don't have this sort of impasse between the two. Well, I was aware, I don't know whether I was told or I thought about it myself, I was aware of the fact that if you take the field of complex numbers, fold them up into a sphere, so you've got a point at infinity as well, and you take the real numbers and think of that as the equator. So the real numbers go around the equator and the complex numbers go up and down. And if you have a function which is defined on the equator, which extends into one hemisphere, that's positive frequency. It extends into the other hemisphere, it's negative frequency. This is a completely conformally invariant description. You conformally invariant the sphere, and it doesn't change the splitting into two halves. So I wanted a way of doing this, but globally for space-time. So for the whole space-time, I wanted it to be somehow that the real space-time is the boundary between two extensions into the complex. But if you just complexify space-time, make all your coordinates complex, you get an 8-dimensional space, not a 5-dimensional space. So that's no good. It doesn't split it into two halves at all. You get a thing called the forward tube, which is a little tiny thing at one side or the other, in which you can talk about things being regular there or not, but it doesn't split anything in half in the same sort of way. So it didn't satisfy me. I don't know why. I mean, what was I doing? It didn't seem to have any rational reason for looking at this. But it did seem to me there ought to be a way of exploiting this beautiful way in which you do the positive and negative frequency without having to look at the Fourier components individually. It's a deeper concept, if you like, and it's also conformally invariant. So the scale business that Maxwell theory has, you don't lose that. Okay, well, I had this sort of going around in my mind and didn't know what to do about it. It was a very unfortunate occasion because I was in Texas, in Austin, Texas, and I was working with various colleagues in Austin, Texas. Engelbert Schucking was running this particular meeting. It was a year-long meeting where people like Roy Kerr, Ray Sachs were there too, and very distinguished people working in relativity theory. And there were also people in Dallas, Texas, and one of them in particular was somebody I was collaborating on a book. I don't think I was doing it at that time, on spinors, and this was Wolfgang Rinder. And Ivor Robinson, who was also, he was somebody who was a very clever fellow, had wonderful ideas. He never wrote anything down. He relied on getting a co-author to write the paper. It was all done with words. He was had a wonderful way with words. The Americans loved him because he spoke in this way that they weren't used to, which the words all fitted together in this beautiful way. Yes, he did have a wonderful way with words. There's no doubt about it.
Was he the one that didn't write papers?
Yes. But he was important in another story, which is a different story, with my story, namely the singularity theorem, because that was walking down the street and crossing the road. That's a different story. It was the same person. That was Ivor Robinson. Yes. So he obviously was somebody who could take my attention. But what he had told me about was he'd found some solutions of Maxwell's equations, which had a very special character. They're what are called null. They have point in one direction. You see, usually there you have these two directions, which are called principal null directions, on the light cone. They're light directions. And if they coincide, it's what's called null. And these are more like radiation fields. And he found a beautiful family of solutions, which he constructs it in the following strange way. You take a light ray, one light ray, and you take all the light rays which meet it. When I say a light ray, I mean the trajectory of a photon. So in space-time, it's the space-time picture of a photon. That's thought of as a particle. So now if you think of one light ray, and you look at all the light rays which meet it coming in, then you have a family of light rays. But they're light, and then he constructs this solution which is based on those light rays. Now they have this awkward singularity, which is the light ray that they meet.
Why is that a singularity?
Well, they all start coming together, and so they're not. The nature of the solution is different when they come together. You see,
okay, but it's of a different sort of singularity than the singularity theorem.
It's not a serious singularity. It's a singularity in the Maxwell. I think things become infinite.
I see.
I don't remember the details of it.
Sure.
They just become infinite of that solution. Just because the light rays don't make this nice family anymore, they got crunched up on the other light ray. But what Ivor Robinson did, he had this clever trick where you just place the light ray into the complex, make it a complex light ray, then you can keep the light rays which meet it. There's a family which is still real. So you can see those real ones, even though the one they meet is in the complex. And they twist around each other in this wonderful configuration. I thought about this before, and I think I knew in detail what this configuration was. It corresponds to what's called Clifford parallels. Clifford parallels are a beautiful geometrical configuration. If you take a three-sphere, so that's an ordinary sphere, but in 4 dimensions. So it's a three-dimensional surface in 4 dimensions. So it's a family of points which have the same distance from the origin in 4 Euclidean dimensions. I'm not talking about space-time now. That 4 Euclidean dimensions. So you have a three-sphere, and there's this beautiful family of circles which fill the whole three-sphere. No 2 of them intersect, and they all link each other. It's called Clifford parallels, or it has a name which is the topological people like better. Well, it's called the fibration.
Right.
And it's a sphere's worth of circles. It's a very nice example of a fiber bundle, and how you have this diagram that people like to draw, where you have the fiber, which is the circle, and the bundle, the entire bundle is the sphere, and the projection down is the 2-sphere. So each circle corresponds to a point on a 2-dimension, an ordinary 2-sphere, an ordinary sphere. So the points, each point corresponds to a circle. So it's a beautiful example of a fiber bundle. It's the most simple and beautiful example you can have in a way.
New update. Started a Substack. Writings on there are currently about language and ill-defined concepts, as well as some other mathematical details. Much more being written there. This is content that isn't anywhere else. It's not on Theories of Everything. It's not on Patreon. Also, full transcripts will be placed there at some point in the future. Several people ask me, "Hey Kurt, you've spoken to so many people in the fields of theoretical physics, philosophy, and consciousness. What are your thoughts?" While I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. Also, thank you to our partner, The Economist.
Sir Roger Penrose. It's been a long time coming. I've been a huge fan for, I think, decades, literally decades. Thank you, and welcome.
My pleasure.